Hi, today I'm going to talk about the solutions for Atcoder Beginner Contest 420 problems A to E and G. And let's start with problem A. For problem A, we're given integers x and y between 1 and 12, and we want to find what month it will be y months after x. And what we can do is we can directly add y to x, and then we can modulo this by 12 to get the remainder when the value is divided by 12. And because we want the month to be ranging from 1 to 12. So when we get a remainder of 0, we want to change that to 12 because that's the month we want. And now let's look directly at the code. So here's the code for problem A. I first inputted the values x and y, and then I added y to x, then as what I just said, I modulo x by 12. So when we get x is equal to 0, we change this to 12 because we want the months to be ranging from 1 to 12. And then we output the answer. Next, let's look at problem B. For problem B, we have n people and each person gave n votes where the votes are either 0 or 1. And the votes are given as strings of length m. So there are n strings of length m that represent the votes. The jth character represents the vote person I gave for the jth votes. And in each vote, people who were in the minority receives 1 point. And what this means is that when X people chose 0 and Y people chose 1, then if X is smaller than Y, people who voted 0 will receive 1 point. And otherwise, people who voted 1 will receive 1 point. In the end, we want the output that after all the M votes, we want to output all the people who have the highest total scores, with the scores calculated from here. What we can do is, because n is small, n and m are both small, so we can just directly loop through all the votes, and for each vote, we can check whether 0 or 1 is the minority vote. Then we can use an array to keep track of all the scores for all n people. Then in the end, we just find the maximum score. And let's look at the code. Here I first inputted n and m, then I inputted the strings which represents the m votes of each people. And here we loop through I from 0 to m, and this counts the vote for each of the m votes. Then here we loop through each person from j from 0 to n, and then we count the number of ones casted for all the n people. Then we do this count. Well, we check whether count is greater than n minus count to see which number is the minority vote. So if count is greater than n minus count, then this means that 0 is the minority vote, and we would loop through all the n people to see which ones voted 0. If they did, we would add 1 to the scores array. And the scores array keeps track of for all n people, the scores for each of them. And otherwise, 1 would be the minority vote, and we will add 1 to all the people who voted 1. In the end, we find the maximum score, and we output all the people that have this maximum score. For problem C, we have length n integer sequences A and B, and we want to process Q queries in order, where for each query, we have a character C and integers x and v. If C is equal to A, we want to change AX to V. If C is equal to B, we want to change BX to V. For each of the queries, we want to output the sum of the minimum of A and B for all k from 1 to n. To do this, we don't want to recalculate the sum for every query because this would exceed the time limit. However, we notice that for each query, only either AX or BX would change, meaning that the remaining values all remain the same. So we can keep track of a sum, and then for each query, we subtract the sum by the previous value of min AX BX. Then after we change either AX or BX, we again add the minimum of AX BX to this sum. And to make it more clear, we can look at the code. Here I first inputted n and q, then I inputted arrays a and b. Then I first find the current sum from looping from 0 to n of all the minimum of a and b. Afterwards, I process the queries, first inputting the characters c, x, and v. Then, because we're going to modify ax and bx, we first subtract our current sum by the minimum of ax minus 1 and bx minus 1. And we minus 1 because the index that the problem gave us starts from 1, while the index we use starts from 0. In this part, we subtract the previous value of the minimum of ax and bx, so we can add it back after we process the current query. And then here, this part, we change the values according to the problem, where it says that if the character is equal to a, we change ax to v, and otherwise we change bx to v. Then this part, we again add back the minimum value, which will be based on what we changed here. Then we can output the answer. This way, we won't have to recalculate the sum every time, and we would just need to subtract and add back the value for the current x index. For problem D, we have a grid with H rows and W columns, and for each cell, there can be several states where the dot represents an empty cell, and this symbol represents an obstacle cell. S represents start cell, G represents goal cell, O represents open door cell, X represents closed door cell, and a question mark represents a switch cell. So we can move to an adjacent cell in 4 directions up, down, left, and right. If the next cell is not an obstacle cell or a closed door cell. So the closed door and open door cells will change whenever he moves to a switch cell. So when we enter a switch cell, all open door cells become closed door cells, and all closed door cells become open door cells. So we want to determine whether we can move from the initial state, which is the start cell, to the goal cell. And we want to find the minimum number of operations required to do so. For this type of problem where we're operating on a grid and we want to move from a start cell to an end cell, and with a minimum number of operations, we think of using BFS. And we can do BFS by storing the current location that we're on. So I, I and J, and also the parity of the number of question marks we stepped on. So this for K, we only care about whether it's even or odd, because if we step on question marks for even times, then they cancel out and equal to stepping on it none of the times. So we can record a DP to keep track of, for each location ij, the minimum number of operations needed to reach ij when the current number of question marks we stepped on has a parity of k. This is really important because if we don't record the number of question marks, then this wouldn't capture all of these states, because the state we're on for an odd number of question marks is different from the state we're on when we stepped on a even number of question marks, because the open door and closed door would be the exact opposite. So we need to keep track of both states to ensure that we account for all the possibilities. And if you're not sure how to implement a BFS, we can look at the code. So here, this is my DP. It stores the I, J, and then K, where K is just 0 or 1. And I first inputted all the values in my array A, which is a character array. Then, because I want to do BFS, I used a queue, and I created my own struct called S, which includes SY, XY, step, which is the number of operations, and dir, which I store with the number of question marks we step on, so the parity of the number of question marks. And when aij is equal to s, then this means that this is our starting point. Then I first filled all the DP with a maximum number, so this way we could find the minimum easier. Then I changed DP ij 0 because initially we stepped on 0 question marks, and we're at the start cell I and j to 0 because this takes 0 steps to reach this. Then we push this into the queue so that we can do BFS. And this part is my BFS implementation, where I first popped out the value that we're currently on, and then if the step is already greater than what is stored in the DP, we continue, because then that means that it's already not optimal because we want the minimum value. And if we reach G, then we can just end, because this means that we've reached our goal with a minimum number of steps, because we're using BFS. So this means that it's definitely the minimum. Then this part is looping through all four directions. So we loop through all four directions, and then we add the directions according to what's defined here. So new y, ny, and x represents the new x and y coordinates. This if statement checks with if we exceeded the grid. So we don't want to exceed the limits of the grid. So if we do, we just stop it. Then if it's this symbol, then it means that it's an obstacle cell. So we don't want to go there. Then also, this part depends on the parity because if we stepped on a even number of question marks, but a new x new y is equal to a closed door cell, then this means that it's still a closed door cell, so we can't go there. But if we stepped on a odd number of question marks, then open door cells would be closed door cells, so we can't enter there. These steps would be the previous step, which is recorded by S step 1, because step is stored here. And this part keeps track of how many question marks we stepped on. So if this current cell is a question mark cell, then we would add 1, then we would continue to mod this by 2. So if the number of steps is less than what we currently have in the DP, then we can update this and post this into the queue to continue our BFS. In the end, if we found something, we would have print out the answer and stop the program here. So if we haven't stopped, then this means that it's impossible to reach the goal, and we output -1. We then move on to problem E. For problem E, we have an undirected graph of with n vertices and 0 edges. So the vertices are numbered from 1 to n, and initially all of them are colored white. And we have Q queries to process where the type 1 is to add an edge connecting vertices U and V. Type 2 is to flip the color of vertex V. Type 3 is to determine whether black vertex can be reached from vertex V by traveling some edges. We need to output yes if it's reachable and no otherwise. This problem resembles a disjoint set union problem because it involves connecting the edges and also checking whether some edge is reachable by another edge, which is what a usual DSU supports, because a usual DSU supports uniting vertices and checking if they're in the same component, which is similar to what this problem is asking, except that this problem also includes the fact that there are two colors, black and white, and when we want to check, we're not checking for two specific vertices, but one vertex and whether it's connected to a black vertex. So this gives us the idea that we want to use a DSU, and to modify the DSU to match this problem. For the DSU, when we're uniting the vertices, we also need to keep track of an array to store the number of black vertices in each component. So what we want to do is, for the DSU, we keep track of some array, maybe in this case, I called my array rank. Then this would store the number of black vertices in the current component. And when I encounter a type 2 query, Then I just subtract rank by 1. If if it was if it was originally black, I switch to white. Then I subtract rank by 1. But if my color was originally white, I do the opposite and add 1 to rank if it was originally white. So this means I also keep track of a bool array called color to keep track of whether each vertex is black or white. And this means that because if we had a rank that keeps track of the number of black vertices, for for the type 3 query, we can just directly check whether the rank is 0 or not. So if it's 0, then this means that it's not reachable to any black vertex, and we will output no. But if the value is non-zero, then we will output yes. And we can look at the code. So here's my code, and this part is the DSU implementation where I first set all the rank to 0, and this represents the number of black vertices because everything is initially white. It's all set to 0. Then this will be modified later in the code, and this part is combining. So I combined. When I unite the edges, I also combine the ranks to ensure that the rank represents the whole component. Here I inputted n and q, and if the type of operation is equal to 1, we just directly unite the vertices where we use our function defined above. Then for type 2 queries, we also keep track of a Boolean array to keep track of whether the vertex is black. Then if it is, we subtract the dot rank by 1, and d dot find v is just finding the ancestor of the group. So we find this group, this component, and then finding the ancestor. Then the rank of this will represent the number of black vertices in this whole component. So we subtract this by 1 and set the color to false. We do the opposite if the color is already black. If the color is initially white, I mean, then we add 1, then set black to true. For type 3 queries, when we want to output, then we just check if the rank, again, we find the ancestor to see whether it's greater than 0. So if it's greater than 0, we output yes. Otherwise, we output no, which means that there's no black vertices that are connected to the current vertex. For the last problem, we talk about problem G. This time, we're given a integer x, and we want to find all integers n that satisfy the constraint that the square root of n squared plus n plus x is an integer. Let's look at how we can simplify this problem step by step. So if we want the square root of n plus x to be an integer, then we can see that this needs to equal m squared, where m is an integer that's greater than or equal to 0. When we see this m squared and this type of problem where we want to find integers, we want to try to find its factor. So we want to try to factorize it, and because we want to try to factorize it, we want to have both sides have these type of squares where we can use to factorize the number. So we want to combine these ones with n into one square item so we can factorize it. Because we do this, we want to multiply this by 4. Then this will give us 2m squared. Then if we multiply this into this, we get 4n squared plus 4n plus 4x. Then since we want to make all the items with n into one single whole square, so we can do this where we combine these items into a square item like this. Then we do plus 4x minus 1. Because this part we get an extra 1 when this is expanded. Then we get our desired square item, then we can move this here, then expand this into 2m minus 2n minus 1, multiplied by 2m plus 2n plus 1. Then we can get our desired factorization, which would help us solve this problem. So since the answer we want to find n, then if we see that this whole thing is defined as A and this thing is defined by B, then n would be equal to B minus A minus 2 divided by 4. Then because A and B are factors of 4x minus 1, in our code we just have to factor 4x minus 1 considering both the positive and negative factors. And we need to remember one thing, which is to use long because the range of x is from negative 10 to the power 14 to positive 10 to the power 14. So this exceeds the value of integers, so we need to use long to prevent overflow. Next, let's look at the code. So this part, I first inputted x, then large X represents 4x minus 1. We find the absolute value of this so we can find the factors. Then we loop through I until I squared is less than or equal to the absolute value of x. Then if I is divisible by this value, then we can find j, where j is abs x divided by I. And then so this we find both factors I and j. And now we just need to check whether they're either positive or negative and assign them to A and B, which was just what I mentioned before, where A and B are like the factors of 4x minus 1. So we first decide to assign A to positive I. Then we check whether the big X, which is 4x minus 1, is positive or negative. So if it's positive, we give B positive j, otherwise we give it negative j. Then we find n, which was just what I showed before, would be b minus a minus 2 divided by 4. Then we insert this into our answer vector, which we would store all the possible answers for n. Then we tried the other alternative, which is if a is negative I. Then if x is positive, big X is positive, we need to use big X and not small x because we want to find the factors of 4x minus 1. And so we need to use this to check whether it's positive or negative. So if x is greater than or equal to 0, we use negative j so that when a, b are multiplied together, we get a positive value. But otherwise, we use j to get a negative value. Then we use the same calculation to find n. Then we insert this into answer. Because in the end, we get a set of possible values of n. Then because we want it to be sorted, we sort this, then erase all the repeated values to find the unique order of n that are possible. Then we just output the answer. Thank you for listening to today's explanation.